Çalıştayımızın öğleden sonra oturumuna devam ediyoruz. The next presentation comes from Dr. Andrea Himilevski, IAEA former section head at Department of Nuclear Science and Applications and director of Institute of Nuclear Chemistry and Technology from Poland. He has three presentations. First one is flue gas treatment using electron beam. Second one is volatile organic compounds treatment using electron beam. The third one is examples of radiation technology for zero waste circular economy. Welcome, Andrea. The stage is yours.
Thank you. Merhaba, good afternoon. So welcome. I thank you very much for inviting me to this meeting. I appreciate very much Omer action. You know, he was working so hard also in agreement concerning this our presentation. Of course, the support of TOMO and TC, International Atomic Energy Agency, is very important because the speakers are coming this way. So I am very happy. Also, I was very pleased to hear the presentation of your Director General, because you are developing very interesting science, high-tech science, and in many places it is very similar what we are doing in Poland. So even we agreed to discuss this matter and collaboration. We have some already collaboration. So everything is coming all together, that it is nice and good to be here. I was visiting Institute, but maybe 15 years ago, and also Turkey maybe 3 times in different locations. But now I am very happy to be together with you back. And I have this free presentation, but I may say that already some aspects of this problems which I will cover were discussed, so it will be easier, but maybe I just will concentrate on the matters which was not yet set here, and especially about this environment protection, because we are saying very easily, yes, we have to just protect the environment, but going deeper, maybe even about these green parties which want to do something, but sometimes they don't understand very well problem and also technical solutions. So we should do this. So I will just move by myself. This is just, yeah. So the first, my presentation is flue gas treatment. I just pressing this, how it works. It's changing. Oh, yeah, that's right. So, you know, we should start. As a matter of fact, this slide was behind me when Sunil was showing his presentation, and we had this lecture in Warsaw, in Poland, with big number of participants, and we are saying, okay, we have to save environment, but why? Of course, if we look on this different, you know, atmospheres, just Earth, this is mean temperature about 1330 degrees, Venus 450, even it is woman, but it's not nice to live there, and Mars minus 53, so some people are going already there. There will be not very easy life. So of course Venus is, because this greenhouse effect is very high, so even the water was just dissociated, and hydrogen, oxygen went somewhere in the cosmos. And Earth, what we need. But we have to remember that if we look for Earth and make it like apple, the skin is atmosphere, and we are living in the skin. So that's not too much. And on the other hand, you are paying for gas, more. You are paying for water, but not for air, not for oxygen. So everybody is saying it's for free. What is the problem? So of course there are many problems because of the emission of different pollutants, like in the combustion processes. And somebody is saying, even very important people, greenhouse effect. I don't believe. But it's not problem to believe or not to believe. It's just important to just ask scientists about that. You see here in the I'm just looking for pointer. Oh yeah, you see here this molecule, 3 atoms molecules. All atoms which have 2 molecules like oxygen, nitrogen, no problem, because they are transparent for infrared radiation, not absorption. All molecules which has 3 atoms in molecule, they absorb infrared radiation. That means they heat atmosphere, CO2, SH4, H2O even, and so on. So therefore, we have to fight with them with these different solutions. And Sunil already mentioned that seems to me that nuclear energy is the best solution for this problem. But we have another problems that still we have to use coal. So even countries nowadays in Europe, because oil is, especially gas, it is not so much available, are shifting to coal again. So of course you may use coal, but you have to clean these flue gases. Because you have from the emission of flue gases SO2, you have NOx, of course you have CO as well, and also these organic pollutants, maybe in the coal combustion not so big, but in the oil bigger. So anyway, this is these problems concerning that we have to make some let's say, purification of the flue gases. And you know, this is the purification system in the conventional application. That means normally catalytic reduction, where you are using ammonia, unfortunately, some substrate, and later on you have FGD for absorption of SO2. It is normally a wet limestone process. So you see, you have very big, here is boiler somewhere. Oh, boiler is here, and here you have wonderful chemical factory. I am happy about that because I am also professor at University of Technology in chemical engineering. So my students, they have a lot of work to be done also in power industry. But unfortunately, you are getting also some problems like even with gypsum. Of course, gypsum can be used for the wall boards, but for example, in Poland, if we would produce only gypsum from that, we'll get something 3 million tons per year. And of course, also you will just dig our lime, different calcium minerals, which also are used for other purposes. Yeah? So this is not easy problem to be solved. So this is this electron beam, as already Sunil just was referring to that, but I add only here to this his presentation that of course we have here ionization of these flue gases. You have heard also about plasma processes like corona discharge, but you should remember that in this our case we are using electrons of the energy something like 600, 800 kiloelectronvolts, yeah? But in the corona discharge is less than 10 electronvolts by the electron, and in this case you are just sending this your energy to the vibration and also rotation energy, these factors, not to the, let's say, moving of electrons for reaction. So this is the reason that, for example, in the plasma process, like corona discharge, you have to use for one molecule of NO for oxidation to NO2 something like 70 electronvolts. In our case, 18 electronvolts. So that means that consumption of energy is much lower. You have to remember always also that the work is not done by the primary electrons. Normally in the material you are getting a lot of the secondary electrons, and these secondary electrons are doing job, yeah, in principle, in your case. Of course, this is very important that this chemistry is in favor of us. And secondly, also in the flue gases, you remember that density of flue gas is something like 1.27 kilograms per cubic meter, and water 1,000, yeah? 1,000 kilograms per cubic meters. That means we may use these low energy accelerators, what is fantastic because these are the atmospheric type accelerators, transformer type accelerators. So the energy efficiency is very high. I will not go through the reaction, but anyway, these are the reactions which are behind. But anyway, we are getting the mixture of ammonium sulfate and ammonium nitrate, which is fertilizer, yeah? And with this reaction with ammonia, so first we built this kind of the pilot plant. So somehow this part just refers to the interesting presentation by Dr. Bajdemir this morning when he was talking about scale up. So also in the case of chemical engineering, you scale up by 10. For example, so when we started with laboratory 1,000 cubic meters, later on we went 10 times higher, 20,000 cubic meters, and finally we went to 270,000 meters, so 10 by 10. So this is also from the technical point of view because you have to elaborate different components. Here you see that, of course, we have radiation chemists, but radiation chemist is not good enough. You need also some chemical engineering, other specialists from accelerators, etc. So this is very important. Oh yeah, I may look just here. So we applied also to this, oh sorry, so this W irradiation, you see the two accelerators are in the series, one after the second. You see this way we are able to increase the efficiency by 10%, what is very important. Of course, I will not go in details, but anyway, this is also coming from chemistry of the process. And after that, the next one, 10, here we have a little different chimney than in the case of Sunil presentation, but the power station is the same. But here we applied these accelerators for 270,000 cubic meters per hour, and power of accelerators was 1.2 megawatts. 1.2 megawatts for accelerators altogether. So here we applied also this W irradiation, and you see here how this electron beam was scaled. But also interesting here that even we are scaling along the flow of the flue gases. You know, here we have the vessel in which the reaction goes this way, that this is steel. That means that you have also ground potential. So that means that even we are scanning this way, these electrons are going everywhere, yeah, because there are secondary electrons. So you are getting, if we made some photo, you have plasma in all cross section, what is also important for these findings. And of course, the removal efficiency was very high. The removal efficiency of SO2 is easier than NOx, so most of the energy goes for the reduction of NOx in this case. That means this NO oxides. But very important is that this byproduct collector, we were getting fertilizer for good application. There is also solution, wet solution, that instead of electroprecipitators, of Dr. Tan was working on that, and it was Turkish solution and American solution, where you have the kind of the scrubber in which you are getting in the water this kind of the byproducts, but later on you have to just dry them. This is already mentioned by Sunil. This was our project together with Bum Suhan when he was just the president of the EBTech company, so accelerator came from them. The engineering and all details came from Poland, and all together we in the Aramco, Saudi Arabia, we have done such test for the oil-fired boiler as well. So this is general view, but in this case, this mobile accelerator has been applied. What is interesting for different application. Also in Brazil, they have such mobile plant for the wastewater treatment. They just study in different location. But nowadays it's funny. In Europe, the best big problem concerning emission is emission from the ship. You know, such big ship like these cargo ships, or even this just passengers, this big type of ships, they have a diesel engine, something like 80, even 100 megawatt. That means that somehow we have to treat. And you see on this bottom here on the bottom, that nowadays emission of SO2 and NOx is bigger from this kind of the transportation means than from the power station, because most of the coal power station in Europe, they have already gas treatment systems and not these vessels, yeah. So anyway, here we have to apply something. Here together also here we have Dr. Yongsa Sun with me. So all together with her laboratory, we developed such solution, hybrid solution for the application on the floating vessels. And this application has been tested in the field of shipyard, Latvia, where we applied the flue gases from this type of ship, and this was done together with the Fraunhofer Institute from Dresden, so low energy accelerator came from there, and also the University of Riga. It was in frame of the European project, which was coordinated by CERN in Geneva. So anyway, we got good results showing that it's possible to application. And nowadays, this Fraunhofer Institute in Dresden is working on toroidal accelerator. Also, I know the news from the United States, they are working on something similar. And you see here in this case, you have emission of electrons from all around the flue gases flowing inside of the pipe. So special solution which is very wonderful for the application for flue gases treatment. No, so this was what I was going very fast with the application of these electron beams, because also I will follow this in this electron VOC treatment. So some aspects already were discussed in the presentation of my colleagues, so I don't like to go again through that. So if I may ask for the next presentation is on the VOC. Omer was just referring to the emission of a VOC, which is also a big problem. Okay, so this is about this volatile organic compounds treatment using electron beam. This is a big problem. And also what I may mention concerning SO2 and NOx, everything is coming from the regulation. If we are not have regulation, you know, any industry is giving money for nothing, yeah? So they don't care about the environment. But when they are getting limits, for example, like in Poland, if you don't have the, let's say, some treatment installation, one of the manager came to me, you know, even on this small boiler, we have to apply the some kind of the flue gas treatment. I said, but how big money you need. No, altogether 170 millions. Do you have this money? Not, no, of course we have to find this money, but we have to do it, because otherwise our installation, it is heating installation, will be closed, yeah? So there is no solution. The same with this ship of gases treatment. You know, already are existing such emission control areas, ECM. This is Baltic Sea, also the Atlantic close to the North America from both sides, and also very soon will be here Mediterranean Sea. So the ship without treatment of flue gases cannot enter this sea. And for example, in the United States, if your ship will come there and will emit SO2 and NOx, for 1 day will pay something like $20,000 fines. Yeah. So when I was discussing with Grimaldi, they have this big passengers type of the ships. They say that some of them cannot just sail to the America for this reason, because it would be too costly. So that means that you have to do something with that. Also the same with these volatile organic compounds and the treatment using electron beam, that in very beginning nobody was looking for these VOCs, but of course these VOCs are more toxic in some cases than even this SO2 and NOx, yeah. Of course you don't forget also about this PM2.5 in the case of these combustion processes, but we again, we may. Oh yeah, okay. It started, yeah. So this is also with Dr. Sun and Dr. Ostapchuk. They were making their PhD on that, and so in case this is the definition. So volatile organic compounds, it's any kind of organic compound which is just emitted in the process, but especially dangerous are so polyaromatic hydrocarbons. And one is very important, that if you want to go with the study, or if you want to apply it, for example, at the incinerator plant, because as you remember, when it was opposition against the nuclear energy in Europe, the next one were municipal waste incinerator, because about dioxins, yeah. The people afraid, they didn't like to have close to them this incinerator. So that means that this kind of the pollutants is very dangerous, and therefore EPA just introduced, and also this International Health Organization, they introduced some limits, but also here, if you are working on the measurements of the concentration, it's better to apply not the concentration, but toxicity equivalent, because that means that not each has the same toxicity. So you have to just multiply your concentration by toxicity factor, yeah? And after that, you know, because sometimes in the process, also sometimes in the electron beam process, from one kind of pollutants, you are producing some other organic compound, yeah? So that just to see if this process is effective, you have to measure concentration and find out toxicity equivalent inlet, outlet, and those moments you know it. Of course, to get rid, because sometimes it is PPBs, so get rid of, to go to zero, almost is impossible in any technology. So that means that, of course, you have some kind of limits, and you have to meet these limits. So, in combustion process, you have complete combustion, so you are getting CO2 and H2O, is okay. Though, of course, CO2 is still, but the concentration is not so high, so concerning greenhouse effect is not maybe such a big problem. But unfortunately, in complete just combustion process, so especially if you have lack of oxygen, so for example, always this lambda in the case of the coal boilers should be bigger than 1, just the ratio of the carbon to the oxygen, yeah, a little bigger. And then also the low temperature of combustion, so also you, in the case of these municipal incinerators, even you have the second stage to heat gases to higher than 170 or 40 centigrade, because these dioxins in such case are destroyed. And of course also the time of residence time of the fuel in burner zone, yeah. So in the result of complete combustion, you are getting different CO and VOCs, oxidized form, aldehydes, and also alkanes and aromatics. But this is not the end of the story, unfortunately, because these are the simple organic compounds. You see, the combustion process is just good plasma reactor. So you may make synthesis of such compounds which do not exist in fuel. Yeah, somebody says, oh, I have very good anthracite, just coal or something like that, or wood, I am using wood. From wood also we are getting such. In this just flame, in this plasma reactor, you see that you can go to benzoalpha-pyrene. And for benzoalpha-pyrene, this toxicity factor is 1. And some are bigger, some are less than 1, so depending what we concerning this. And then everywhere you have chlorine, yeah? Even in your food, unfortunately, even this, and sodium chloride is not good for our health. So very quickly also you are getting formation of this CH also bonds, and that means that you are getting also formation of dioxins, which are even more terrible as let's say toxins concerning the cancer, etc., like this other compounds. Now what happened with this my no, but why you don't show you? I don't know, because, oh yeah, because you know, probably they defended themselves, because I want to show how terrible they are. Because normally, you know, we don't know, but even these not living creatures are just forming something which is not good for us, yeah, unfortunately. So here you see this DNA, yeah, with these 2 chains, yeah, over there, DNA. And this benzoalpha-pyrene has just dimension exactly like this bonds between these 2 chains of DNA. So it is very easily incorporate that there, because why? Because you remember that these 2 chains are just bonded by hydrogen bonds. The most low energy, low, let's say, stability bonds. So our life is really related to the something, the very, very, very not, let's say, strong something in bonding this our DNA. This is the reason why you hear about these gene changes, etc., in DNA, etc. So this is the reason, because it's incorporate exactly between these two bonds, and later on we have some modification, so normally it goes to cancer, for example. Yeah. So this is the reason how our pollutants are even worse than we just think. So of course we may try to just destroy them with different type of let's say processes. So for example, just such a process like conventional one is most known is adsorption, yeah, by adsorbent. So let's say in one year, EPA or especially DOE funded some research to find a way how to remove these organic pollutants from combustion of gases. So they granted maybe something like 15 projects just to look which are possible to be applied. But unfortunately, concerning the adsorption, you have to just blow this adsorbent into the flowing gases, what of course is not easy, because you remember that in the case of the exchange of the mass between the air or flue gas and solid, you have to have very big surface of contact, yeah? Because diffusion in solid is very slow. So of course one block of this sorbent is doing nothing, because beside of the reaction we have to remember mass transfer, yeah? Mass transfer, especially concerning the, let's say, also the diffusion coefficient in gas very high, in liquid also not so bad, but in the solid state sometimes years. Yeah, so that means that this is also important, and the problem was not easy to be solved and was not solved. But in different institutions, also in Poland, in Germany, in Belarus, in Japan, Belarus, especially in the modeling in the United States, etc. Such experiments were done and still are done. And concerning our application, we first started with the pilot plant. This was this pilot plant in which we were using this process for SO2 and NOx removal, and we were interested if also in this case we have some emission of these polyaromatic hydrocarbons, and also if some of them and how much of them is adopted in this fertilizer. So we have done also these experiments, and of course in this case the problem concerning the measurements of the SO2, other gases, dust, ammonia, sleep, etc. is quite easy, because you have different instruments, infrared, let's say, instruments, or special instrument with UV emission. But concerning this very low concentration of volatile organic compounds, we have also the emission of, I mean, the methods are rather based on adsorption. So, because the concentration is so low that normally you have one instrument on the inlet for the sampling. So one is in the inlet sampling point, and also the second one is outlet sampling point, and we are using the adsorbent. So after just getting some time, we just flow some given volume of the flue gases from that. Also, that's very important how we are getting these samples by the isokinetic just sampler, just to be sure that we are making just this as a mean concentration in this flow. And later on, of course, the analyses are in the laboratory. Yeah. Analytical procedure. So the first is pre-concentration. Then we are using sorbent. Then extraction from the sorbent goes to the toluene extract. Then separation and gas chromatography. On this basis, we are getting just what kind of organic compounds are present and what is the concentration. If somebody is interested, Professor Yongxia Sun is with us, so you may just ask her concerning what type of instrumentation and of kind of sorbents they are using. So concerning the just this boiler is not still end of this different VOC treatments. Just concerning this coal combustion, fortunately the emission of the these pollutants is not so high because the combustion process is rather high temperature, so most of them are just incinerated and destroyed. And also that also very important what we just found it, that these polyaromatic hydrocarbons concentrations are not depend on the power of the boiler, and also the contribution of benzo alpha pyrene and benzenoanthracene is not so high. This is very important. For us also it was important that in our byproduct we had no just pollutants, but also you have to remember that this fertilizer which are produced in chemical industry, for example ammonium sulfate, which is used as well as a fertilizer, is produced in the caprolactam industry, and it is just waste stream, so it has something like 2% of different pollutants inside of such. So this our process is rather very pure process. Also, some people are asking what about the heavy metals. So because we have a dust collector in the front of this our electron beam, that means that we have no just fly ash in that, and that means that the concentration of the metals is very low because they are just inside of this fly ash. Also here we have heard, I think that somebody mentioned about that maybe some industry just afraid radiation. Of course, the radiation itself, electron beam is something like, you know, which this TV tube, which I see everybody is young, but in my time we had not such TV like now, plasma TV or liquid crystal TV. It was tube. And in this tube is the just emission of electrons, exactly like in our case. But nowadays still you depends on the electrons, because I think that from time to time you have to go for the X-ray examination, yeah. So that means that in such case you have Röntgen tube. In Röntgen tube you have emission of electrons, and later on on anti-cathode you are getting X-ray from that. So everybody from us knows what accelerator is. So of course when you switch out, the accelerator is not working and anymore, no problem. But also, you know, probably you have the same. Sometimes different authorities are coming to your office. So for example, we had control, there is such the high chamber of control, and the guy came just for audit. Nothing wrong happened. I am ending before going to conclusion. But he also took somebody from Environmental Protection Agency. And this guy from Environmental Protection is asking, no, Professor, may you write us that your byproduct is not radioactive? I said, you know, I may write to you that this byproduct doesn't contain any heavy metals and something like that. But if you ask me about this, what you said, that means that I have to return my diploma to the university, because that means that I was taught not so well. Because you know the electrons of energy 800 keV cannot just induce any radioactivity. And this is the reason also why for sterilization we are not going further than 10 MeV, yeah? Just not to get induction of radiation. So this is the in the product, of course. So everything should be just considered. So this is, on the other hand, municipal waste incinerator. So beside of the combustion is so not high because this is not coal. This is just garbage, so also this calorific value is not so high like in coal, so also temperature is not so high. So first of all, you are getting a lot of SO2, and you are getting also a lot of dioxins as well, because in garbage you always have this chlorine somewhere, just from the use or from something. So here is the big problem of these dioxins, and at the end you have to have sorbents for these dioxins, yeah? And it is rather not good waste because these dioxins are adsorbed on that. And especially big problem is, and in principle, as I understand in China, of course we have heard also about this wastewater treatment from hospital waste. But another problem is the waste in these red bags, yeah? You know that hospital, in principle, this biologically contaminated waste cannot just throw on the municipal waste, let's say, storage. They have to put them in this red bag, yeah, and later on for incineration. But what is inside, especially when we had this COVID, yeah, 30% is plastic, these syringes, single-use syringes and something like that. Nothing better to form this kind of this dioxins, yeah. On the other hand, the incineration plant, sometimes some hospitals, they have own incineration plants, or maybe smaller, just are bringing to one place somewhere. But the flow of the flue gases in such case is very low, up to 20,000 cubic meters. So similar like in our this pilot plant which I mentioned in Coventry. That means that here application of this technology is quite viable, yeah. And I think that I have heard that, of course, I was once in China. Just I was asked to go from one place to the another, just to discuss with them application of this kind of technology. And here it would be good because in this case you need just one accelerator, let's say something like 50 kilowatts, but transformer accelerator, that means the electrical efficiency 80%, something like that, energy up to 700 kV. So that means that also the accelerator is not so very expensive, and this is also very good application. So you see here is quite big just installation needed. So here you have this formation of this different type of the dioxins, and this kind of dioxins which are normally formed during the combustion process of municipal waste were investigated in Japan, So this is the plant in Japan where they applied this accelerator for the irradiation. But beside of the let's say electron beam accelerator, there also applied charcoal, because you know the limits are just PBBs, not ppms, even PBBs. So that means very low concentration is allowed, and is good, because this is very, very dangerous toxin. So this is the plant built in Japan for this application, and you see that it was self-shielded accelerator 300 keV, and self-shielded accelerator of 300 keV is interesting solution. Of course, it is already applied in many cases for the polymers treatment, because in this case I think this accelerator may stay here, be in operation, and nobody is hurt, yeah, because it's already so-called self-shielded. That means that is like in this doctor room, just in this case they use some steel or some lead just to cover this accelerator, and some let's say workers, they don't even know that this is accelerator, some electric device, and here this kind of accelerator was applied. So here you see the chemistry of this process. So in principle is detachment, because electrons are very like the family just is attached to chlorine, and it is just disattached of these chlorine atoms. That means the same compound without chlorine is not so toxic like with chlorine. So sometimes it's not necessary to destroy fully some kind of organic pollutants. Just if you make change in the structure is good enough. And with those rather high dose, about 30 kilograms, but normally you are not need to go to such concentration, to such efficiency. I think it was nice presented by the Dr. Ergun, that also she was showing at which dose is possible to get quite good efficiency, because it is again comes from the chemistry, from chemical engineering, that let's say for 95% you are paying some with energy, yeah, and for the next 2% you are paying the same what you paid for 95%, non-story. So you have to just adjust to the limits. Always you have to follow what are the limits. Yeah. Also, sorry. So this is our laboratory stand. I may just say that here we are using this our stand for the just study on the different polymer treatment, but also the flue gas treatment, but also treatment of wastewater. So this is ILU-6 accelerator. The energy is about 2 MeV, up to 2 MeV. We may go down, and 20 kilowatts. And what I may say that now we got such project from the European Union. It is so-called Eurolab. That means that we are in the net of different facilities in Europe which offer their installation for the the students and scientists from outside of laboratories. So for example, if somebody is interested to go to our laboratory and make some research, it's necessary to prepare some kind of the project and later on to present to the committee which does consider this project as interesting. So later on this group or scientist is funded for the, let's say, travel, per diem, and also experiment times, yeah, just in our lab, so all are invited also to use opportunity. Also this concern other laboratories, because it is but not all of them, they have electron beam. In principle, we are electron beam. There are proton, there are other types of the accelerators also open for the people from Europe, and also some percentages for the people from outside of the Europe. Concerning the laboratory research, we were concentrating on the influence of the process dose, temperature, humidity. Always is important on the removal efficiency, distributed of the products of the composition, and also process mechanism. No, and of course the higher dose and lower concentration just are good for the removal, higher removal efficiency, and also the components of this flue gases influence of the process. And because here, just coming a little back to this flue gas treatment, in principle your electrons are not reacting or influencing these pollutants, because concerning the radiation technologies, your ionizing radiation energy is just absorbed in the proportion to the mass factor of some component. So if the, let's say, SO2 and NOx are ppms, of course matrix is more important. What you have in matrix. So you have in matrix different pollutants, you have also water, so especially water is very interesting, because from water you are getting OH radicals. And these OH radicals are just reacting with this SO2 and NOx. The most important reaction for SO2 is oxidation to SO3, because together with water and ammonia you are getting ammonium sulfate. Concerning NO is terrible to be removed, because it is not soluble, non-reactive. So that means that you have to oxidize NO to NO2 just to get reaction with water, and you are getting nitric acid. Yeah? Later on, in reaction with ammonia, you have ammonium nitrate. Ammonium nitrate together with ammonium sulfate is very good composition for the fertilizer. You have to add just little components with potassium, and you are getting so-called phosphorus, and you are getting so-called NPK fertilizer. Yeah, so that means that this is the reaction. So here you should remember that in the flue gases, this plan, this is the different reactive species, free radicals, also some ions. All of these free radicals, OH. If somebody is not working in the radiation chemistry, maybe good to say what is the free radical, because of course everybody knows what is ion. Ion is having one electron more than needed, yeah, minus ion. If it is positive ion, that means that deficit of one electron or more, depending what kind of ion is. Just this free radical is, for example, O2. If we have O2 and we separate O from O, this is as in family, yeah, the husband and wife. So altogether here, O2 is very good also for us, living together, but sometimes they separate. And in this time, they are very reactive, looking for other, species around and reacting. That means, what is the difference? That means that, of course, in the last orbit, they have only one electron, or depending on the kind of the atom. But so they just borrow, yeah. They have money altogether. Is just more better to live, yeah. So one electron comes to one electron. I mean, in principle, they are all together, like in family, yeah. They have joined two electrons, and this is what it's like. These rings are keeping them together. So that means that this is not, let's say, ion, but very reactive. So why we have in just atmosphere O2, not O, O2. Or we have N2, not N2, yeah. So that means that life is coming also similar in our case, yeah. So that means that here the reaction is not done exactly that we heat this molecule, which we want to do something. I think SO2 and NO, not necessary. Just other radicals, other ions are doing this energy to them, and later on we are getting reaction products, yeah? So this short story about free radicals, yeah. But, you know, chemistry is alive. So we are using, for example, this kind of different compounds, and also this irradiation was done in the batch system, but also flow system. So you may discuss with Yongsha if you are interested how it was been done. And there was also just study on these different types of the pollutants, which are very important. So here we have very interesting story, because in principle we may treat in one single process 3 different pollutants, SO2, NOx, and also organic pollutants. So difficult to find similar technology which may in similar way treat this all kind of pollutants. Of course, this is very also important to get this removal of these pollutants which just contain this chlorine, because I just was referring to that this is very, these are these dioxins and other pollutants which have to be removed. So the most on my display, excuse me, you may do something with, because I see all the time, Bill glass size, sesi ile kata, something. I don't know. Okay, now it's okay. Now I see the same what you see. So the main reactions are positive ions neutron reaction, negative ions neutral reaction, ionic recombination reaction, radical reaction. So we know now what radical is, and radical neutron reaction. So this is kind of the reaction is going here. So you see that chemistry of these processes is not easy. Of course, sometimes solution comes first, because sometimes it's easier to make experiment to find something than to get just theory. So depending, sometimes first theory first, experiment next, sometimes experiment. What is time? Yeah, it's already. Yeah, no problem, because you know I am also professor at university, so I may talk all the day, so I have to be stopped. Yeah. and one moment. When the last student is leaving, I am just finishing my lecture. So I don't like to check the same here. So anyway, this is these different active species are formed. So in this different reaction, and here you see that this is the work of Yongsha. So this is how this process is working. So not easy process. Of course, you have to go here everywhere for the kinetics reaction, because not all the reaction are with the same velocity. Yeah? And you remember from chemistry that the slowest reaction are influencing the whole process later on. So that means that this is very important just to make this reaction. So this is what we find it out, what kind of the organic compounds may be treated by VOC. So in principle, most, I think, if not all, but many of these different pollutants. Of course, the different are used and also, for example, it depends on the bonding. If two bondings or one bonding between the atoms, it's also influence the process. Yeah. So in principle, it's possible. But also very important work is being done by our colleagues from Korea, that here in this process you may apply some kind of the hybrid process between the electron beam and also catalyst, yeah, just to reduce energy needed from the power, rather, needed from the electron beam. So here is also very important that if we are talking about this different application, which we heard from very morning today, sometimes it's good to think about the combination of the processes. You have seen from Dr. He from China that they were working on this COD, also using biological process. The same was on in Korea, in Bumsuhan installation, and also electron beam. So altogether, you are getting better process. In this our process for the flue gases treatment, in the case of this marine diesel of gases treatment, we were using also the scrubbing process. Why? Because in many cases, and also in this case of NOx removal, for the higher concentration of NO, you have also back reactions. So for example, you are getting NO oxidation to NO2, but if you are making higher dose and condition change, you are having also back reaction. NO2 goes to NO and O, because normally most of the reaction, especially in gaseous liquid phase, is reversible reactions. Yeah? So somehow to get equilibrium moved to the right side, to the product, you have to remove products, yeah, somehow. So if we are scrubbing NO2, still the concentration of NO2 is low, and reaction goes right side, and this way we may just get better efficiency. So here is good examples how the experiment is supported by the theoretical work. Yeah, so all scientists are important, both experimentalists and also theoretical guys. So this is what we have to remember. So this was also done for this off gases in the case of this ship of gases, and you see that also in this case there was some emission of different pollutants, but fortunately most of these pollutants, as you see, this emission and later on before AB and after AB together in this combined process was possible to remove most of these pollutants. So beside of SO2 and NOx is very important just to clean this off gases also from these pollutants. So here is very story, even being here already I am discussing with some industry application of these low energy accelerators. And you have to think about that also in your institute, because these machines are not very expensive, and in principle it is electron beam bulb. Like you are buying bulb for here, Also, this is a bulb with some lifetime they live some time just, and later on you not repair them, just you exchange like your bulb here. But this emit up to energy 300 kV. And for example, Tetra Pak, you know Tetra Pak, this for different juices, etc. They are using online for sterilization. Because in this case, you don't need, of course, bulk sterilization, big bag, you have to go to 10 MeV. But if you just want to produce foil, or you want to sterilize just the surface or foil, yeah, in such a case you need not so high energy, because still we remember the density of air is not so high, 1.2 kilograms per cubic meter. So penetration is quite good enough, yeah, something for 200 kV, 25, 26 centimeters. In water, just microns even. So that means that you may apply this in different applications, and what we are discussing nowadays with company in Poland, and I like such people, because this owner, he wants to get something new in his, because he is producing different type lines for the filling, producing and later on filling bottles with juices, yeah? Such like, especially for children. Juices like lady in the, this way it looks like. And nowadays they are doing this way, that this is extruder, yeah, you are getting bottle goes on the line very quick, and later on they put some finger with the hydrogen peroxide in the steam form, yeah, just inside. Later on it goes up, next rising, next just drying, and further juice going in. And here the same can be done with electron beam in one shot, yeah, because in principle you just irradiate, you got sterilization of the surface and go to the juice. Not necessary rising, not necessary drying, yeah. So he is present. Today I got two emails from him, if this good or not good. This electron beam is produced in the E-beam company in Switzerland. It is a low energy accelerator, so this kind of accelerators are used by the Tetra Pak. And here you see how simple is the power supply, yeah. In this another, when somebody was visiting us, the operator is sitting, yeah, the two cabinets and so on, but here is just on your desk, yeah, so even for experiments on the surface curing is good to get this. And this was applied in Korea. Already they are just selling this Puristar. This is how this instrument looks like, and this is for odors, yeah. This is the problem of odors, especially when even in the towns when you have kebab or something like that. No, kebab maybe is not so bad because you are feeling good smell, but there are smells which should be not felt. So that means in such case, the, let's say, off gases is not so high. It's something like 15,000 cubic meters, which you have to pass through something. But in some cases, adsorption is used, so of course you have to use this active coal or active coke, for example, for adsorption. Here you have very similar installation like in our this SO2 and NOx treatment. And this is the installation itself, how it looks like. Accelerator is inside, yeah. So this is how it works. And this is what is the future, and I think that it's good to think about also application of these low power accelerators. So this is the second and the last one for this afternoon. One left. One left. How it is hard to Chmielewski. Still I have time because it's already so I maybe go very quick. Yeah.
Can we
Shift it.
right now we are in coffee break? Seems.
Coffee. No, so coffee break, you cannot fight with coffee break, for sure. But you know, you are so nice audience, I am looking here, interest in the eyes, so I may talk to you all the day. So sorry for that.
Can we finish it in 10 minutes?
Okay, in 10 minutes. Let's go. Because here, in principle, I want to refer what was said before. Because we already agreed on the environment protection. We agreed that we know why we should just protect the environment. Now, this is not solution still, because we have already heard about this plastics garbage. Yeah, I mean, we have seen very nice presentation also from Omer and also from other presenters. So nowadays we have to just work on this circular economy. And it came in European Union, but in principle it is for everywhere. No, stay here. So anyway, that means that we should have no waste. So nowadays we want to have circulation, you know, also concerning municipal waste, yeah. We have to separate the different items and later on to recover. And you know, some years back we were very happy that we had a lot of raw materials. Nowadays some metals, for example, are critical metals. We have not enough them. So that means that we have to go to, so even concerning this air, already we are using fly ash and bottom. Fly ash goes to this, you know, the bricks and different types, and also the flue gas desulfurization. So here a very good example was this production of fertilizer. So in principle it's the same what I said. Only the philosophy is different, because at very beginning, where we started 20 years back, we were just thinking to get pollutants back down. Yeah, but nowadays we know that we may use them. Why to just make new waste? Yeah, so this is this fertilizer. You see this just application of this fertilizer, how it is prepared later on to be sold. Water and soil. Water, nowadays we have big problem concerning the water, because we are using a lot of water to different application, etc. So somehow if we don't use the same water once again, it will be the problem. But in principle, we are using already the same water, but maybe not in good manner, because, for example, as you know, Vistula River is our main river in Poland, coming from the mountains, going to the Baltic Sea. First is Kraków, the very old our town. It was capital many years back. Yeah, so they are drinking this water from Vistula. Later on, the wastewater is coming back after some treatment and goes to Warsaw, where I am living. So then we are drinking this water, yeah, and of course we treat them, and then it goes to Gdańsk on the Baltic Sea. So they are drinking this water, and then it goes to the Baltic Sea. So it's better maybe that some components may be kept with us, yeah, or we in Kraków, because, for example, not everything should be drinkable water. Some water we can use for something. Yeah, this is a very simple example. When I was in Japan, it's very simple. You know, we are flushing our WC. Yeah, and and after that we are washing our hands somewhere. Yeah, but in their case, the next water coming to this reservoir is just to wash your hands, because you know this toilet bath is on this washing reservoir. Yeah, simple, but just half of water is used. So this how we have to remember. Today we had very interesting presentation how to just save this water, because you see here the shortage of the water in the world. This was in 1995. This is above over there. Here you see the regions. Unfortunately, Turkey, also Turkey, also is somewhere here. So also the problem of drinking water and fresh water everywhere. So. Of course, the wastewater, somehow we have to recover this wastewater, yeah, and that I will not go through in detail, because I understand these slides will be available, yeah, for participants, yeah. So anyway, I don't go through the process, but in principle, it is what we were discussing today even, that we have this wastewater treatment, just here, then disposal of sewage sludge and utilization of biogas energy also from this. Also, the Sunil shown how much is this sewage, a lot, 1 million tons in Europe. But this is fantastic fertilizer, but have to be safe, yeah. So we have to just remove this biohazards from that, yeah. So later on. Of course, nowadays you cannot just make sludge disposal, landfilling, no more. Also, in some years back, there was sea dumping, just then dumped to the sea, not terrible. Yeah, so anyway, here we are using two processes of radiation chemistry. One, water radiolysis for the wastewater treatment, the second, biological treatment on the right. So, of course, this is also some solution concerning. This was what we have seen. So that means that from here we are getting back water, but we have to do something with sludge, yeah, as well. So that means that nowadays in some countries this sludge is already used, but parasites are in that. So especially when you are using for agriculture, especially tomatoes, strawberries, no, later on without just washing is rather not very advisable. So in principle, the zero is content of parasite. This is how we are studying this in our institute. So already we heard that Lalit will talk about gamma. So anyway, with electron beam is also to do the same. So some afraid how these bacteria survive. So in some cases, we may just apply terminal sterilization process. Terminal, all is killed. But better not go to so far, but if somebody afraid. So this is parasites which are present, unfortunately. in principle, so we have to go to zero. You should remember that also in the sludge you have phosphorus compounds, up to 3%. Phosphorus is not recyclable, so if it will go to the sea, we will never recover this phosphorus, and phosphorus rock is also limited in the script. Here is answer to our lady who was talking, Dr. Ergun, who she put the question how it is with the paracetamol, this kind of the type of the DCF, which is drug in drugs. We made study how we may just destroy it. It is in wastewater and in sludge. So unfortunately in sludge is 50% of that what we may achieve in the wastewater, because some of these compounds are just incorporated in sludge. But it's still lower than in just and here we also, for accelerators, we are using so-called zero technology. So that means that we make hygienisation of the sludge, but also electricity from biogas. Oh, I think it was said this morning, are used for this. This I will come very quickly. It is about ballast water. So anyway, that we have to work this way, no more linear approach, circular approach, please, and thank you very much for your time. Thank you.
Dear Andrea, thank you for your presentation. Kısa bir aradan sonra devam edeceğiz. Çalıştayımıza kurumumuzdan emekli fizikçi Sayın Doktor Erdal Tan'ın örnek çalışması ve yakıtların baca gazı arıtımı isimli sunumu ile devam ediyoruz. Erdal Bey'i davet ediyorum sahneye.
Merhabalar, herkese iyi öğleden sonralar. Tüm misafirlerimize hoş geldiniz diyorum. Beni de buraya davet eden eski arkadaşlarıma, herkese çok tekrar teşekkür ediyorum. Tamam. Profesör Himilevski işin kimyasını oldukça detaylı anlattı. Ben çok fazla üzerinde durmayacağım. Biz elektron demetiyle baca gazı temizlenmesi çalışmasının Türkiye'deki pilot tesis bir uygulamasını anlatacağım. Bu tesis TÜPRAŞ'la beraber yaptığımız, orada üretilen fuel oil'in yüksek kükürt oranlı %3,5'luk içindeki SO2 ve NOx'in giderilmesiyle ilgili bir çalışmaydı. Burada ilk önce bir tesisi kısaca başlayacağım. Yapılan deneylerden kısaca bir deney ve sonuçları size sunacağım. Bu elektron hızlandırıcımız ilk başta 2009 yılında geldiğinde kurulduğunda self-shielded dediğimiz kendinden zırhlı küçük bir odacığın üzerine kurşun çelik konstrüksiyon. Şu ön tarafı açık görünüyor ama tabii normalde açık değil burası. Şurası açık değil. Burada da zırhı var tabii kurulum sırasında. Bu şekilde kuruldu. Sistemi çalışır şekilde teslim aldık. Böyle gördüğünüz gibi elektron hızlandırıcısı üstünde, altında küçük bir odacı, güç kaynağı ve soğutma ünitesi, kontrol ünitesi burada kabaca görünüyor. 2007'den 2012'ye kadar bu şekilde kaldı. Fazla bir deney yapamadık çünkü amacımız orada cihazın depoda yıllarca beklediği için bir an önce teslim alıp çalıştırmaktı. Elektron hızlandırıcımızın tipi şöyle bir şey. Şurada elektron hızlandırıcısının tüpü var. Burada saptırıcı bobinler. Burada tarayıcı dediğimiz. Şu da elektronların çıktığı pencere. Bu bir titanyumdur. Bütün elektron hızlandırıcının çoğunda bu tip titanyum pencere vardır. 50 mikron kalınlığında. Bu da 5'e 60 santimde boyutlarında 50 mikron kalınlığında titanyum pencere. Cihaz 350 ile 500 kilovolt arasında enerji verebiliyor. Akımı da 1 miliamper ile 20 miliamper arasında değiştirilebiliyor. Bu tür bir cihaz. Bu tesise nasıl başlandı? Biz TAEK ile TÜPRAŞ arasında 2010 yılında elektron demeti teknolojisinin baca gazı temizlemede kullanılması üzerine bir protokol yaptık. Bu Türkiye'deki bu konudaki ilk çalışmaydı. Burada TAEK'in katkısı, o zaman TAEK'ti ismi, o yüzden öyle söylüyorum. Çünkü ben de oradan emekli oldum. Elektron hızlandırıcısı, bina, insan gücü olarak bir fizikçi ben vardım, bir kimyager arkadaşımız vardı, o ayrıldı. Bir teknisyenimiz ve kurulum süresince sürekli bize teknik servis sağlandı kurumumuzca. TÜPRAŞ'tan ise binanın güçlendirilmesi ve yenilenmesine ilişkin, orayı yarın ziyaret olacak, göreceksiniz. Onunla ilgili çalışmalar, bir kimya mühendisi arkadaş oradan katıldı bize. Vivrat dediğimiz bir firmamız var. Fransız firması. Bizim hızlandırıcıyı aldığımız. O firmanın birazdan göreceğiz gaz reaktörünü tasarlaması. Bu toplantılar yapıldı TAEK, TÜPRAŞ ve Vivrat arasında. Onun dışında gene TÜPRAŞ gaz boylarını, baca giriş çıkış su hatlarını, amonyak hatlarını, pompaları, tüm analiz ölçüm sistemlerini satın aldı. Bu tabii bu kendi bütçeleri artı TÜBİTAK projesi kapsamında ve deneylerin bitiminde de tüm bu şeyleri bize hibe ederek ayrıldı. Tabii bu cihaz 2010 yılından 11 yılın Mayıs'ına kadar bu tasarıma yönelik çalışmalarımız yapıldı. Daha sonra paslanmaz çelikten gaz reaktörü yapımı başladı. Bunu takiben, tarihleri söylemiyorum zaten görülüyor. Elektron hızlandırıcısı mevcut halinden söküldü ve binanın güçlendirme çalışmaları başladı. Bu kapsamda ayrıca baca gazı giriş çıkış hatları, iç dıştan gelen bütün borular, içerideki su hatları, amonyak su enjeksiyon ve emme pompaları, bunların aksesuarların alımı, elektron hızlandırıcısı tekrar monte edildi. elektron hızlandırıcısı birazdan göreceğiz. Bir zırhlı bir 70 santim duvar kalınlığı olan bir odanın üzerine, tavanına yerleştirildi. Kendinden zırhı çıktı. Sadece üst kısmındaki zırh kaldı. Pilot tesisinin elektrik bağlantıları yapıldı. Bilgisayar sistemleri ve aktivasyon testleri. Bunun takibine analizörlerin bulunduğu elektron hızlandırıcısı binasının dışında bir kulübe gibi bir yer daha yapıldı. Fuel oil kazanı deposu, bir de boiler kuruldu. Bunların ön testleri yapıldı ve çalışmaya Ekim'in başında 2012 yılının başladık. Yaklaşık 1-2 yıl devamlı çalışmalar yapıldı burada. Bu o göreceğiniz yerin inşaat hali. Burada şurası işte gaz reaktörü, Vibrat tarafından tasarlanan gaz reaktörü, daha tasarım sırası imalat sırasında yerleştirmeden önce bu odanın üst kısmı, gaz reaktörünün diğer bölümü kurulmuş hali böyle. Şurada tavanı var. Hızlandırıcı da bunun üstünde. Boiler'dan bir görüntü. İşte şu yukarıdaki bu halden bu hale getirdik. Şurada bir 70 santim duvar var. Kalınlığı yaklaşık 2.65'lik ortalama yoğunlukta betondan yapıldı. Bu bina yerin altında olduğu için yan taraftaki zırhlamalar doğal olarak toprağın altında olduğu için, zeminin altında. Yan tarafı sağ, sol ve arka tarafı zeminin toprakta olduğu için zırhlamaya gerek kalmadı ama beton duvarları var tabii. Elektron hızlandırıcımız bu odanın tepesine yerleştirildi. Soğutma üniteleri ve güç kaynağı bu şekilde. Bu da yaklaşık 9 ton ağırlığında, yanlış hatırlamıyorsam, bir kayar kapımız var. Yapılan tasarım bu şekilde. Tabii reaktörümüz, hızlandırıcımız gaz reaktörünün üzerine yerleştirilmiş. Baca gazımız geliyor. Amonyak ve suyu gönderiyoruz. Bunları da kısaca değineceğim. Daha sonra buradan yan ürün olarak Profesör Himilevski'nin bahsettiği gibi gübreli sıvı halde gübre elde etmiş olduk. Bunun nasıl olduğunu anlatacağım. Sistemimizin genel görüntüsü böyle. Şurası kazan, şu analizörlerin bulunduğu bölüm. Bu binanın dışında büyük bir yer, göreceksiniz yarın. Bu yerin altına doğru, binamız öyle olduğu için hızlandırıcımızın ve kayar kapının olduğu yerin altındaki bölmeye gidiyor. Şimdi baca gazı kullanan kömür, fuel oil gibi kullanan termik santraller, rafineriler çıkardıkları SO2 ve NOx gazlarıyla ve havadaki nemle birleşerek asit yağmurlarına sebep oluyorlar. Baca gazı temizlemede halihazırda dünyada uygulanan desülfürizasyon ve denitrifikasyon tesisleri var. Bunlar ticari ve endüstriyel boyutta birçok termik santralde ya da yukarıda bahsettiğim endüstriyel tesislerde baca gazını temizlemek için kullanılıyor. Bunlar kendi aralarında işte yarı kuru, ıslak, seçici katalitik indirgeme ve benzeri teknikler kullanıyor. Bu tamamen işin kimyası ile ilgili. Benim çok uzman olduğum bir konuda değil. Mr. Himilevski zaten bundan yeterince bahsetti. Şimdi bu iki işlemin bir arada kullanılması, yani desülfürizasyon ve denitrifikasyon tesisi, bunlar esasında termik santral için kullanılması bir kere yüksek işlem maliyeti, daha geniş alan gereksinimi. Yani termik santralinizin yanına bir denitrifikasyon tesisi, bir de desülfürizasyon tesisi kuruyorsunuz. Baca gazını temizliyorsunuz tabii ama. Daha çok insan gücü. Bunun sonunda da çıktığında gene temizlikten sonra asitli su, kireç taşı, karbondioksit ve diğer kirleticilerin üretilmesi ve bazı tekniklerden dolayı da katalizör kullanılması gerekiyor indirgemelerde. Bunların maliyeti var. Bunun dışında bir önceki konuşmacımızın da belirttiği gibi baca gazı temizlemede birçok teknik, yeni geliştirilen teknikler var ama mesela plazma tekniği. Bu daha yeni lab scale'de devam eden bir çalışma. Şimdi bu çalışmalar esasında 1970'li yıllarda ilk olarak Japonya'da başlamış. En güzel uygulamalarından biri daha sonra Polonya'da var zaten. Daha sonra bu çalışmalar dünyada birçok ülkeye endüstriyel boyutta ve pilot tesis olarak yayılmış durumda. Elektron demetiyle baca gazı temizleme. Elektron demetiyle baca gazı temizlemede yapılan iş, baca gazını ilk önce konvansiyoneli artık oluyor teknik, yani alışılagelmiş olanı baca gazı teknolojisinde şu anda. Elektrostatik çöktürme, nemlendirme, daha sonra bu şeye amonyak ekleme ve karıştırma odası, daha sonra bu şeyi Mr. Himilevski'nin anlattığı gibi elektron demetinin uygulandığı reaktörün altına gönderip bunun karşısında işlem bittikten sonra çıkan yan ürünü gene elektrofiltrelerle toplayıp yan ürünü almak. Bunun avantajları ne? Bu tür bir sistem, elektron hızlandırıcısı teknolojisini kullanıyorsanız denitrifikasyon ve desülfürizasyonu tek bir cihazla, sistemle yapmış oluyorsunuz. Yani iki ayrı tesis kurmuyorsunuz. Tek bir tesisle hem sülfürleri hem nitrik oksitleri sülfür oksitleri ikisini birden temizlemiş oluyorsunuz. Yani simultaneous denitrification and desulfurization'ın amacı bu. En büyük avantajı da bu zaten. Bunun yanı sıra gene organik bileşikler, buna benzer diğer kirleticiler de bu sistem sayesinde temizleniyor elektron hızlandırıcısı sayesinde. Burada da gene yan ürünü olarak en büyük özelliği gübre elde etmiş oluyorsunuz. Güvenilir bir işlem, işletilme daha kolay, konvansiyonel biraz önce bahsettiğim tekniklere, desülfürizasyon, denitrifikasyon tesislerine göre daha düşük yatırım maliyeti ve işletme maliyetleri var. Şimdi burada işin detayına çok fazla girmeyeceğim. Gene burada amaç yüksek enerjili elektronu amonyak ve suyun olduğu bir ortamda baca gazına göndermek. Elektronlar baca gazındaki azot oksitler, nitrojen, oksijen, su ve benzeri bileşiklerle etkileşerek serbest radikaller oluşturuyor. Bu serbest radikaller de SOX ve NOx ile etkileşerek reaksiyonlar burada nitrik asit ve sülfürik asit oluşumu oluyor. Esasında biz ortama baca gazını gönderiyoruz ve suyu da gönderip, elektronları da gönderip burada bir asit yağmuru oluşturuyoruz. Ama bu asit yağmurunun üzerine, oluşmuş asitlerin üzerine amonyağı da gönderdiğinizde siz gübre elde etmiş olursunuz. Bunlar da işte temel reaksiyonlarımız. Bu konular çalışmalarda, yapılan çalışmalarda göstermiştir ki bu tür sistemlerde Mr. Himilevski'nin katkısı çok fazladır bu konuda. Su miktarının artırılması, doymamış olması sayılır, satürasyona gelmeyecek şekilde. Bu tür şeylerde suyu artırırsanız veriminiz daha çok artıyor. Biz de bu şeyden hareket ederek yapılan tasarımda elektronu uygun miktarda kuru faza nazaran daha ıslak bir fazda, çünkü kuru fazı da birazdan göstereceğim, atmosfer başında doymamış bir gaz akışı içerisinde enerjiyi, elektronları gazın üzerine gönderiyoruz. Bizim pilot tesiste uyguladığımız bir anlamda amonyak, su, gaz hepsi aynı anda sisteme giriyor. Ve buna biz onun için all in one, hepsi bir arada dedik. Bakın şu normalde bizimkinden farkı bir yanma ünitesinden gelen gazı elektrostatik çöktürücülerle toparlayıp ondan sonra su spreyiyle soğutup amonyağı gönderip daha sonra bu karışımı, baca gazı karışımını elektron hızlandırıcısının üzerlerinde olduğu gaz reaktörünün içerisine gönderip elektron hızlandırıcısıyla etkileştirip daha sonra filtrelerle dışarı alıyorsunuz. Buna karşılaştırma amaçlı yaptım. Yoksa birbirinden yani çok iyidir, bu kötüdür anlamında değil. Bu şu anda dünyada endüstriyel boyutta kullanılan elektron demetiyle baca gazı temizlemede kullanılan tekniktir. Biz ise burada tek bir fark, şöyle bir şey yaptık. Bunların hepsini, gazı, amonyağı, suyu, hepsini tek bir seferde bu reaktörün içerisine gönderdik. Reaktörümüzün genel görüntüsü böyle. Tepeden elektron hızlandırıcısı geliyor üst tarafta. Buradan baca gazlarımız giriyor. Bu işlenmiş baca gazı şu iki yan taraftan çıkıyor. Boyuta dikkat ederseniz yani 2 metre yüksekliğinde bir şey. Şu iki kolun arası da 6 metre sınırda. Burada da bir takım su perdeleri var. Fazla amonyak kaybını engellemek amaçlı olarak Buradan da su püskürtüyoruz. O şeyi de göstereceğim. Bakın bütün diğer sistemden farkı, bütün baca gazı, her şey bu sistemin içerisinde halloluyor. Suyu, amonyağı ve gazı tek bir gördüğünüz bu sistemin üzerine gönderiyoruz. Onun için buna all in one diye bahsettik. Şimdi reaktörün orta bölümünde baca gazı yoğun sisli bir ortama amonyak ve elektron demetine maruz kalıyor. Burada oluşan reaksiyonlar sonucu meydana gelen sıvı ve gazlar, sıvı bölüm ağırlığıyla yer çekimiyle reaktörün tabanına iniyor. İşlem görmüş baca gazı da reaktörün iki tarafındaki o dikdörtgen yapılı bacalardan dışarı atılıyor. Burada da orada gösterdiğim şurada şuradaki su perdeleri de böyle bir işlem sonucunda fazla bir amonyağın ortama salınmadan tekrar temizlenip reaktörün içine dönmesini sağlıyor. Bütün yapılan oluşan sıvı bu tabanda toplanıyor burada. Bunu istersek biz burada oluşan gübre miktarını zenginleştirmek için bunu tekrar sistemin üstüne püskürtebiliyoruz. O suları gönderebiliyoruz. Şu genel görünümü. Biraz vakit kalmadığı için hızlı geçiyorum. Bu reaktörümüzün üst taraftaki görüntüsü. Bu kontrol amonyak ve su enjeksiyon pompalarımız. Bu suları da bu tür nozzle'larla hangi kolda, hangi tarafta kaç tane olduğunu göstermek için baca gazı çıkışlarında o curtain dediğimiz şeyler var o dikdörtgenlerde. Solüsyon enjeksiyonu için var. Yani yaklaşık yanlış hatırlamıyorsam şuradan bakarsak 4, 20, 30 yani 40 tane civarında şeyimiz var. Nozzle'larımız var. O reaktöre ve baca gazı girişinde ve çıkışında o su perdelerini bu nozzle'larla püskürterek, amonyağı da suyu da bununla püskürterek reaktörün içine veriyoruz. Şimdi bu sistem tamamen bilgisayar kontrollü. Bu reaktörün gaz akışlarını, bütün su, nem, sıcaklık, akış ölçerler, bu kazanın yanması, her şey bilgisayar kontrollü olarak çalışan bir sistem. Bu cihazların genel isimleri, bu da ekranın orada gittiğinizde göreceksiniz bilgisayar kontrollü ekranımız. Bütün burada gördüğünüz gibi boiler, ürünü topladığımız kazan, reaktör hepsini burada görebiliyorsunuz. Burada tüm akışları, suyu, sıcaklığı, baca gazı akışını, her şeyi buradan kontrol edip her şeyi değiştirebiliyorsunuz bunun üzerinde. Bir de şöyle bir avantajı var, biraz önce söylemiştim. Bu reaktörün altında toplanan VGS dediğimiz o Vivirat firması tasarladığı için patentli kendisine. Orada topladığı konsantre gübreyi, sıvı haldeki gübreyi biz tekrar istersek, zenginleştirmek istersek eğer gübre miktarı iyi değilse tekrar reaktörün üzerine püskürtebiliyoruz. Bunların hepsi kontrollü. Burada sıcaklığı da kontrol edebiliyoruz. Şu reaktörde genelde bacak gazımız girerken 100-120 derece sıcaklığında. Sıcaklığı kontrol etmemizin şöyle bir avantajı oluyor. Bacak gazında SOx'lerin giderilmesi için 80 derecenin altında sıcaklıklar, NOx için de 80 derecenin üzerindeki sıcaklık değerleri gerekiyor genelde. Bunu da bizim oluşan sıcaklık gradiyentiyle aşağı doğru olan bu şekilde sağlayabiliyoruz. Reaktörün sıvı fazla çalışması, yani ıslak tip dememiz, baca gazında bulunan bir takım asılı katı maddelerin temizlenmesine de yarıyor. Ayrıca sistemde oluşabilecek tuz kristalleri ve kuru bir sistem olsa kristaller oluşma ve kirlenme oluyor. Burada devamlı bir sıvı fazla akış olduğu için temizlenmesi de sağlanmış oluyor. Biraz önce dediğim gibi gerektiğinde yan ürünü, ürettiğimiz gübreyi, sıvı gübreyi sistemin içerisinde defalarca zenginleştirmek için de çevirebiliyoruz sistemi çalıştırarak. Bizim örnek burada sadece yaptığımız çalışmalardan, bazı çalışmaların bir kısmından temel bir iki şeyi söyleyeceğim. Baca gazı akış oranını, baca gazı sıcaklığını, hızlandırıcının akımı, gerilimi, amonyak akışı, decantation tank dediğimiz gübreyi depoladığımız dışarıdaki tanktan tekrar reaktöre giren su akışını, bu su perdeleri dediğimiz soğutma ve enjeksiyon, amonyak, su, soğutma perdesindeki sıvı akışlarını da tek tek kontrol edebiliyoruz. Bu yaptığımız bir çalışmanın bir deneysel parametreleri kullandığımız örnek bir fuel oil'in baca gazı değerleri bir deneyden yapılmış tek bir parametre, sadece bir deneye ait. Yaptığımız çalışma sonucunda yapılan çalışmada SO2 %99, NOx'de %80 civarında azaltan bir sistem meydana getirmiş olduk. Yaklaşık görüyorsunuz bu 5 ile 10 dakika arasında bu değerlere iniyor. Bu da dozla SO2 ve NOx giderimi ile ilgili. Doz neden önemli? Çünkü burada yaklaşık bizim yaptığımız deney sonucunda 8 kilogray optimal bir doz çıktı. Bunun üzerine de uygulasanız zaten gideriminiz değişmiyor. Ne kadar çok doz uygularsanız esasında sisteminizde de o kadar çok elektrik harcıyorsunuz demektir özünde. Dolayısıyla burada bir anlamda bir doz optimizasyonu da yapmış olduk. Bu bizim sisteme özel bir şey. Bu ileride de belirteceğim. Bu daha sonra ticari hale getirildi zannedersem firma tarafından. Burada son olarak gübrenin defalarca çevrilmesi sonucu gübrenin konsantrasyonu ve zenginleştiğini tespit ettik. Bu çalışmada sağ olsun Ece Hanımlar, Ömer Beyler yardımcı oldular. Sıvı kromatografi ölçümleri onlar yaptılar. Elde ettiğimiz sıvı gübrenin devamlı sirkülasyon sonucunda zenginleşmesini bu şekilde ölçtük. Şimdi bir son nokta olarak şunu söyleyeceğim. Şu yukarıda bahsettiğim size nitrifikasyon desülfürizasyon tesisi. Endüstriyel boyuttaki bir boyutları yaklaşık bu tesisin böyle 40 metre, 80 metre ve 50 metre. Bu ise bu tasarımdaki bir benzeri bir endüstriyel boyutta ıslak tipte gaz reaktörü kullanılırsa bu ise 20 metreye 20 metrelik çok daha küçük bir alanda oluyor. Bunun tesis çalışmasını ve deneylerin çalışmasının bitirilmesinden sonra bize ilk Fransa'dan Total firması geldi. Arkasından Aramco geldi. İlgilendiler. Zaten Fransızlar kendi aralarında bir şey yaptılar bilmiyorum. Ama onun akabinde Çin'den elektrik termik santral firması geldi ve Fransa Çin'le bu tip bir reaktör üzerinde endüstriyel boyutu için çalışmalar yapıyordu. En son ne aşamada bilmiyorum. Şimdi şuradaki bugün sabahki konuşmacımıza ek olarak ben de bunu buraya ekliyorum. O zaman bu eski bir şeydir esasında. Şu anda dünyadaki endüstriyel ve pilot tesis boyutundaki elektron demetiyle baca gazı temizleme tesisleri. Bir tanesi de işte 2012 yılında kurulan Türkiye'deki bu tesis. Bir de TÜPRAŞ bunun üzerine bizim çalışmadan sonra kendileri için yukarıda görünmüyor ama 350 bin miligram metreküp saatte baca gazı akışı için bir çalışma yapmış. Bunu ben oradan aldım. Elektron hızlandırıcısını o zaman 1,5 MeV toplam yani 1500 kilowattlık bir elektron hızlandırıcısı düşünmüşler. Bunların hepsi tabii paslanmaz çelik reaktörü, fanlar yatırım için 15 milyon dolar. İşletme giderlerinin 5 milyon dolar civarını tezmin etmişler ama burada benim dikkatimi çeken şey yok. Personel giderlerini almamışlar ve 3 yıl içerisinde bunun da geri döneceğini belirtmişler. Burada benim söyleyeceklerim bu kadar. Bir sormak istediğiniz bir şey varsa. Ya biraz önceki konuşmacımız Mr. Himilevski hakikaten bu işte çok iyidir. Biz onun fikirleri bizim bu sistemi geliştirmemizde çok yararı oldu. Özellikle Mr. Himilevski, you had a suggestion related to water droplet screen. This idea was the beginning of our study. Thank you very much for this one. Thank you. Teşekkür ediyorum. Çok sağ olun.
Çalıştayımızda son 2 tane çevrimçi katılımcımızla devam edeceğiz. Profesör Dr. Muhammed El Sheikli. He is the director of the Irradiation and Nuclear Facilities at University of Maryland in USA. The presentation is treatment of PCBs in transformer oils and sediment using radiation processing. Professor, can you hear me?
Yeah, I hear you very well. Thank you. I'm just trying to put my presentation here for
Okay,
you.
we can wait.
Can you see it?
Yes, now you can share. The stage is yours. Thank you.
Very good. Thank you so much. Well, again, thank you so much for invitation, and especially I would like to thank Dr. Omar Kantaglu for his kind invitation for my to give a talk in this important meeting. I'd like to give me 1 second here to, yeah. Well, today I'm going to talk about the issue with the polychlorinated biphenyls, that's the PCBs, and of course how you induce the chlorination of these materials with the electron beam accelerators. I just want to show you though that the polychlorinated, there are about more than 15,000 chlorinated toxic compound in commerce. They're huge materials and it's been used everywhere. The most toxic ones, of course, is the PCB, the polychlorinated biphenyls, and the dioxin. And in my lab, we've been working on the declaration for the PCBs for a long time. I would like as well to show that we like to show you that PCBs is everywhere. I mean, it is in the transformers and capacitors, and because they have a very good fire retardant, so people especially General Electric it was using PCB in oil for the transformer and the capacitors for a long time. And believe it or not, there's about 125 million transformers containing PCB still now isn't being used. And of course, we have as well PCBs in sediment. For example, if you look at the New York, Jersey harbor, you could see a lot of PCBs there. And actually, PCBs now, even they found them in the polar bear in Alaska, because the PCB can be transformed and it's stable. So it's a big issue and a very toxic material and cause cancers and other illness. So the idea here it is to dechlorinate PCB using, of course, electron beam accelerators. People they've been really treat PCB. They use, for example, incineration. But the problem with the incineration is really producing more hazardous materials products. And they use as well an aerobic microorganism, but it takes long time. But of course, here the advantage of the laser radiation, especially gamma electron beam, is of course the reaction is very fast, and you could really dechlorinate PCBs in literally in microsecond or millisecond period of time. So the objective of our work here, and still keep going, and we publish many papers on this subject, and we have 4 PhD students graduated on developing technique to increase the efficiency of the radiolytic dechlorination of PCB in oil, soil, sediment, and water. So in my presentation today, I'm going to present in all these cases. And it's very, very difficult, especially in oil and in the sediment, because the PCB is at very low concentrations, and as well, these materials are literally, it's a dirt. It's not really something very clean to deal with. So we're going to talk a little bit about the water organic first, water surfactant, okay, and surfactant which has been used here to solvolize the PCBs, and it's actually the surfactant which has been used here. It's a food surfactant materials, and of course we use it for the transformer oil and of course the sediments. Usually what you have, of course, with the water, obviously, as probably most of you know, when you irradiate water and the PCB in water, you produce all these radiolytic materials, especially here I'm talking about the hydroxyl radical and the hydrated electrons with these radiolytic yields. And those guys gonna really attack the PCB and cause the chlorination, especially with the hydroxyl radical is very powerful oxidizing species, and as well we have the solvated electrons, which is highly reducing species and can really literally cause dechlorination. Dechlorination of the PCB. In both cases, the electron and the hydroxyl radical here, in this case, has been used to dechlorinate the PCB and make it much less toxic. As well, we could use. As well. We have here electron beam being used, and of course we have the cobalt-60, and as well the pulse radiolysis. In both cases, we use this instrumentation to conduct this research. Here is one of the important things in this slide. It will show you how the hydrated electron coming from aqueous solution from the radiolysis of water to dechlorinate the PCB. This is they call it the electron capture mechanism, and you can see it here. Is that the electron come and kick the chlorine atoms out from the PCB, and that's what they call it reductive reactions. Okay, and as well, believe it here, it's very interesting one. The oxidative reaction, which is based on the reaction of the hydroxyl radicals with the PCB, as well cause in the end dechlorination. So in both cases, we could really get dechlorination of the PCBs. Part of this as well, the electron here the hydrated electron absorbs about 720. So it would be nice to follow the reaction of the hydrated electron with the PCB. Here actually is a pulse radiolysis. Here is a pulse radiolysis results where show the hydrated electron reacting with the PCB with the very fast reactions. And look at the reaction here. The reaction is 3.8 10 to 9 per mole per second, which is literally is very fast reactions and could dechlorinate the PCB in matter of microsecond, literally in microsecond. Compare that, of course, with the chemical like incineration or the microbial treatment. As well, the same thing. After you irradiate, you produce free radicals. And then, of course, that will react with oxygen to produce the peroxyl radicals. Peroxyl radicals here of the PCB undergo as well different type of dechlorination. Here you will see as well the reaction of how we in this case we start enhancing the effectiveness of the radiation on dechlorination of the PCB. Look at this slide very carefully. If I have the slide, if I have no buffer, if I add that PCB and no buffer, I'll see this dechlorination as a function of dose. But if I add buffer and make the samples high pH, especially in the carbonate, okay, you see the dechlorination. I could really reach dechlorination in like 20 kilogray, better than going to about 150 kilogray. And the reason for that, it is because of the electron which coming from the radiolysis of water react with water, with the H3O plus to produce H atoms. While of course with the carbonate, the H3O plus is going to be very low concentration, and that's why you really enhance the dechlorination of the PCB. As well, what we did, because as you know, PCB is very hydrophobic, incredibly hydrophobic, and that's really the problem because that's how it really goes to the tissue of especially the fatty tissue of the fish and fatty tissue of the human being. In this case, to solubilize PCB, to make it more soluble in water to treat it, we use what they call it surfactant. This is a Triton X10 surfactant, and that surfactant actually is the good things about the surfactant is it is they call it food additive surfactant. You find it in many can and things, and we use this one to solubilize the PCB. This is another reaction, of course. Here, look at the dechlorination of the PCB here. Okay, with the dose here as a function of dose, and you could see how we're really enhancing with this type of the surfactant effect. Now, I'm going to just change the subject to this PCB in oil. That's really the big things of the PCB. In oil, as I said, transformers, capacitors, those are huge transformer capacitors for a huge high voltage. If you see them on the highway and things, or the outside, they transfer electricity. Those transformer and capacitor, they contain a lot of PCB, because PCB is good because it's a fire retardant. So to prevent fire for these capacitors and transformers, they use PCB. Now, the transformer is very interesting there. It has a lot of things. The oil, transformer oil, has these type of compounds, have a biphenyl, fluorine, pentathiamine, and other materials, and PCB. So all the idea, those guys, so imagine that, and there are a small amount of PCB in this mixture. So the idea now, how to dechlorinate the PCB with these. So all the idea was actually to enhance the chlorination as well. This is the GCMS result, which shows as well concentration of how the PCB been changed, going from biphenyl dichlorinated and become here. You could see here we have it completely dechlorinated in the oil as well. One of the issues regarding the mechanism is very, very interesting here, because you had the electron coming from the accelerator, or the secondary electron coming from gamma rays. This electron gonna react with many materials, gonna react with biphenyl, gonna react with those materials. Now the question is now how it's gonna go to the PCB. That's our problem here. That's the tetrachlorobiphenyl. This is a very toxic material. But the electron going to be scavenged for these materials. So the idea was this electron really react with those materials to produce anion, and the anion after that it produce. This is the reaction which we are looking for. So you see the electron producing anion by those biphenyls, and then biphenyls actually act with the PCB to produce dechlorination, and that's why we got a very good result in this in this work by just let the anion produce, and that will be through electron transfer mechanism cause the dechlorination of the PCB. This is another reactions here, which look about sorry, with the pulse radiolysis, how much we have declination. Sorry, the reaction of the electrons, how it react with the PCB, and we get as well reaction rate constants. For the reaction rate constant we have the biphenyl minus with the tetrachlorobiphenyl. Tetrachlorobiphenyl is very toxic materials. For dechlorination about 1.8 10 to 8, which is really, really fast. This is good microsecond. You could cause dechlorination. Reaction 2 as well with the chlorobiphenyl. And of course, we have as well with the PCB 54, which is very, very toxic material too. Look at the reaction as well very fast, very fast. In other words, all these kind of dechlorination reaction are very fast when you use electron or gamma rays, even in the presence of the oil itself. This is another reaction that shows. I like to show you exactly what I'm talking about here. Look at the electron, for example. In the transformer oil, literally in the transformer oil, react with the just biphenyl, produce biphenyl anion. You see that biphenyl anions? This biphenyl anions has the capability, okay, to do the chlorination reaction of the PCB. This is the tetrachloro PCB, and you could see here how we managed to dechlorinate samples, dechlorinate the atom from the PCB, and make it from tetra to tri, and then from tri to di, and from di to single, and after that you could get only biphenyl. As well, we use triethylamine, and triethylamine is an excellent reductive quencher. So we use it as well to enhance and we published this paper as well in Environmental Science and Technology, looking at the effectiveness of the triethylamine as a reductive and then how to enhance the dechlorination. Here is the reaction mechanism of how we could really dechlorinate again, this is think about this one as a PCB, this is an aromatic compound, and how that will react in the presence of the triethylamine. This is as well part of the materials here with the transformer oils, okay, and this is triethylamine, and you could see how really we enhance the dechlorination reaction. In other words, we really use very, very low dose rate to complete the dechlorination. By the way, it was a very difficult task because we have to get those oil and transformers from transformers and the capacitors, and it was very, very difficult, especially if you look at those the old ones, to see how much PCB, because there are many of them and hundreds and millions of them, and they are there waiting for somebody to clean them. So the idea was very difficult to grab them and to bring them to the lab, and we use our electron beam accelerators and the cobalt 60 to cause the dechlorination. That's the same thing here as well with the gamma versus electrons. Yeah. And so the complete dechlorination we could achieve because of the formation of the trimethyl ammonium chloride salt led to the solidification of the that's one of the issues which we are facing, and now we're trying here to solve it at the moment. Now, I'm now changing now to the subject, to the PCB in sediment. This is the most difficult things actually in my life to work with those guys, because this is sediment in the river. In 1998, for example, it was estimated that up to 7% of United States watersheds have polluted with the PCB. Think about it here, though, especially in the area of the New York, Jersey Harbor area. It was a lot of PCB on the sediment of the Hudson River. This is the Hudson River. If you've been in New York City and you see you stay in Manhattan, you could see the Hudson River. Hudson River divide Manhattan from the New Jersey area, and it's a huge one. And it has what happened though at the north of Hudson River, GE dumped a lot of PCB. So the bass, the bass, and the other kind of fish absorb. So now we are not allowed to, for example, to fish or do fishing from the Hudson River because of the contamination of the PCB. That's how difficult it is at the moment. So the idea now how to dechlorinate PCB in this Hudson. And now let me show you how much you have PCB in the sediment. I mean, look at this. This is PCBs. There are many compounds. I mean, there are 214 or something compounds, PCBs, and all these compounds, all those PCBs compounds. They are in the Hudson rivers, and it is very, very difficult to dechlorinate them, especially in their. Think about it. The sediment. It is a water and silica, because this is the silica, the core of the ground of the river. So these compounds could be, most of it gonna be in the part of the hydrophobic material, not in the hydrophilic. In other words, the solubility of these compounds in water, it's very, very, very difficult and very, very small. So the idea now how to deal with those guys. Let me explain it in a way a little bit here. This is sediment of the river, okay, and here this is the aqueous part of it, okay. So the idea is that the hydrophobic interaction between organic matter and PCB partitioning from water. So you could see it here. So you have something in between, and to attach the PCB itself to the sediment. Okay, so you could see it coated here with organic matter and organic metal complexes. This is water and this is the sediment. And then through hydrogen bonding, you could see that the silica of the water the silica of the sediment, how it's really being attached to the water molecules. This is the silica here. This is SiO2, which is mainly the, soil and silica, mainly they are SiO2. So the silica and SiO2 attached to the water through hydrogen bonding. That's the water here. And then the water as well attached to the different type of molecules, okay, different type of organic, which is really connected to the PCB. This is dichlorobiphenyl PCB. So that's where you're going to see that you see that type of interaction between the hydrophobic. In other words, between the silica and water is becoming a bridge to hook to the PCB. So the question was, how are we going to solve it? How are we going to irradiate these materials? And what the objective here? How are we going to do that? That was the big issue here. Think about as well the humic acid structures. This is the humic acid structures in the sediment. Look how big it is. Okay, so the humic acid structures in the sediment really attached. This is the humic acid here, attached to the silica, and then after that they are here attached to the PCB. So in other words, the PCB really it is attached to the silica or the sediment through the humic acid. So that's really the challenges which we have here. So the best way was to do it is, let's look at this reaction here, how that will go with the reaction with the PCB. First of all, when we take the water from the sediment, okay, the electron reacting with the sediment with the PCB doesn't really react that much quickly with the PCB. It reacts actually with the oxygen, which is dissolved oxygen in water, and that's a big issue. For example, electron react with the water with oxygen is about very fast reactions. So that will scavenge really the electron, and you need the electron. You really need the electron to dechlorinate PCB. That you could see that's the produce automonas. That's a superoxide, and the electron as well react with H3O plus. So if you look at the back again to the silica here, you see around the interfaces between the water and the silica, as well as out of the pH here, in the grade of pH is very low. So around the sediment, you see the pH. The pH. This is the bulk of the water, which is about natural, about 6.8, say 7 pH. We are a little bit less than 7 because of the dissolving of the carbon dioxide. But in reality, actually, at the interface between the sediment and the water, the pH is very, very low. It goes to about 4-ish, even to 5-ish. Okay, so that's why the question was how to solve this issue. Now, again, remind you again, this is sediment. It means literally a dirt. You take it literally. It's not like you go to the lab and you work with a distilled water or ionized water, so to do the irrigation chemistry. No, this is just a dirt, literally a dirt. So you have to remember that your electrons is being scavenged by oxygen, of course, here, and of course by H3O plus at the interfaces with them, as well as there are different type of materials. For example, if you have manganese or lead or chromium, those react with the electron very, very fast. Look at the reaction rate constants here; they are extremely, extremely fast. So that's why, in other words, these gonna scavenge the material from you. So that's why we need to do this different type of thing. So one of the issue was we look at the suspension with the sediment. So we look at try to extrapolate the PCB with the isopropanol suspension. So you have the sediment and as well, and then of course we have to look at how to extract PCB from it. Isopropanol is a very good material to dissolve PCB in sediment into aqueous. So the idea was to extract literally taking that literally. If I go back again, if you let me go back again here, show you here, the isopropanol is going to take the PCB from here okay, and get it back to the more and more to the aqueous media, because isopropanol, as you know, dissolve in water. So the following was we have the dry marine sediments standard reference material, which comes from this is the material which is, they call it SRM, standard reference materials, which is literally represent this sediment, the sediment in the Hudson River in New York area. Okay, that's and I show you before in the previous slide how many it has 200 and something PCB in it, and the idea, of course, was to extract these materials. The PCB with the isopropanol and buffer. As you know, buffer we wanted to use buffer to make sure the pH of the samples in a way so it will not be affected and not be changed during the radiation. And of course, we use electron beam accelerators and pulse. So this work, with this one, we use electron beam accelerator. The idea of using electron accelerator, not the gamma here, it is because it was a proposal being proposed by the late Marshall Cleland to the state of New York to have a literally electron beam accelerator on a barge, and that barge would move on the Hudson River, and on it electron beam accelerator, and you really withdraw sediment from the Hudson River, put it throughout the beam, and then from the other side go back again to the river. So just you treat it like this. So this is part of a lot of results here. It shows you about different type of the PCBs here, and how that will go with the GCMS here. You could see, for example, the PCB 8 dechlorination, PCB 18, PCB 31, as all of them is going down. This is as well the pentachlorobiphenols here, PCB. This was as well. Now it's very interesting actually. Was once you're producing dechlorinate one PCB, high PCB like octa PCB, it will become 7. The 7 would increase, but the octa decrease, and then the same thing till you get all of them one by one. So it was a very difficult work to do the GCMS with those PCBs. It's a very laborious work, because you take one of them will be transferred to the other. When I mean transferred to the other, a decrease in the grading of the PCB from 8 chlorine atoms will become 7. From 7 will become 6. 6 come to 5 till to make sure there is no dechlorination, and that's what you've seen it here in this one. There's no dechlorination at all. Yeah. This is as well as part of the you could see as well. Now you notice something very important as well here. The dose which has been used is very, very high, up to about 500 kilogray to decrease. This is the concentration of the total PCBs in nanogram per gram, and this is the about, we start with about 100 and about 1,500 nanograms per gram of PCB, which is a lot, of course. In this, and as you irradiate, you could see a decrease. That's the total decrease in the PCB, because all the way to about we went to about 500 kilogray, which is about we went from 1,500 to about 300 nanogram per gram, which is we found it good, because otherwise these materials are going to stay there forever. PCBs are very, very stable, and stays for thousands of years, they said. And of course, it transformed from now we have it now. It transformed from the Hudson River, but now to a lot now. You've seen it now in the Great Lakes, like the Lake Erie and Lake Superior. It has a lot of PCB now, and of course there is some report of contamination of the fish in those lakes. And as I said before, even they found PCB in the skin, or in the tissue of the polar bear in the Alaska, and that's to see how big it is, this issue here. Yeah. So about now, here in this case, about 83% total of dechlorination between 29 congeners of the PCB which we use here. You could see it as well here. you could have it here. The concentration of the PCB in nanogel all the way goes down. Okay, that's this, and then of course the biphenyl, it goes up here. So this is complete dechlorination here with the PCB. Another important thing, I'm trying to quickly go through these. We have as well looking at the slurries solution containing 2-propanol and the slurry containing triethylamine with the PCBs. And the same thing here again for the sediment. And here you could see now we did as well here photolysis to look at see what kind of photolysis we could really get, and we found a very nice this one. So it's not just electron as well. We looked at the quenching of the triethylamine and how it helps for enhancing the like you could see here, for example, you take the electrons. That's I'm sorry, that is the PCB itself. That's when I say aromatic chlorine, it means PCB because it's polychlorinated biphenyls. Okay, and this is the triethylamine, and you can see with the photolysis you get excited, and this is a quencher. The triethylamine is a very well-known quencher. Okay, so it's been used in radiation and as well in photolysis, and you could see you could really get the again you could cause the chlorination of the materials. Yeah. So again with the summary as well we were looking, the idea was actually, because people, they said, why don't you use UV and triethylamine and compare it with electron beam accelerator and cobalt-60. I mean, that was really the idea here. The real problem with UV as well, as you know, the penetration. So you have to have the sample very, very thin. But still, we did it, actually. We did it. So we compared the UV with the electron beam. So you talk about UV sources with what was 300 watts in power, lamp placed with the 10 centimeter away from the samples, and look, pay attention to this one. It took us 1 hour, 115 hours, 115 hours, okay, to dechlorinate and that will be equal to 200 kilogray. 200 kilogray with the PCB, with the electron beam, I could make it in a couple of seconds. Literally a couple of seconds, I could finish it. So you could see now the difference between how radiation is much by far more effective than the photolysis. And look at this hours here. This is 115 hours here. I could make it here in a couple of micro to millisecond. I'm done with it. So it is very, very important to look at these things, in my opinion, because there are some now tendency now to use electron beam. I'm sorry, to use UV rather than electron beam. But again, there's two things here with the photolysis. It's this issue of the penetration, and as well, of course, the slow reactions. And as well, we use as well another surfactant that's the ethoxyalkylated sorbate. This is as well another food additive materials, and we look at as well with the conversion and the dechlorination of the PCBs in the sediment. And obviously, again, this is a big issue here. If I look at, if you see it here, it's so complicated, this system, because you have here the PCB, okay, and then of course this is in sediment, and this is hydroxyl radical coming from electron. So electron, okay, so the electron, the kinetics of the electron really reacting with the PCB. That's what you're looking for. But again, you act with the oxygen, reacting with H+, reacting with metal and surfactant. So that was the big things in this issue. But still, you could really control the condition, reaction condition, so you could really enhance the dechlorination. This is as well with the marine sediment and the T-20. This is the other surfactant. You see as well some dechlorination here. So with summary, I would like to come to the summary of this work. The oxidizing powerful of radiation and the in both cases the reductive from by the electron and the oxidation by hydroxyl radicals are extremely important for the dechlorination of the PCB. Other important things as well. It is the how the And when you work with the PCB, it is extremely important whether you do it with oil, with the transformer oil or sediment or organic sludge. It's very, very important to have the carbonate buffer, because that will keep the pH high, so the electron doesn't react with H3O plus, reacts really with the PCB. So really you shift the competition reactions to the dechlorination. Obviously, we have an issue with the oxygen, but the oxygen still is of course, again, as I said, it inhibits the dechlorination by compete for the electron. And it can be done with the surfactant, okay, as well with the surfactant, and they are very cheap surfactant as well. And of course, we compare the work with the photolysis, and we found it is effective. Indeed, the photolysis is effective for dechlorination, but yet it cannot really compete with the electron. This is just a pulse hydrolysis setup with that, and this is the oil. Summary of the oil of the reaction with the PCBs. And this is the procedures, how difficult it is to extract PCB from the sediment. This is the standard procedure of it with the extractions as well. And you could really go through different type of system to so this is the final results which we have with the sediment. And with that, I would like to thank you so much for your kind attention. Thank you. I'll be happy to answer any question.
Is there any question? Yes, one question.
Ben sesim alabiliyor musunuz?
Mikrofon.
Sesim geliyor mu?
Kimiz siz? Chat baksana bakalım.
Hello.
Hello, yes.
Yeah, Professor Mohammed, good evening. I am Lalit Varshne. I hope you remember our 2001 meeting.
Yeah, I remember you very well.
How are you?
Nice talking to you.
And
Nice talking to you.
I compliment you for excellent presentation.
Oh, you're welcome.
I just wanted to ask a small question or query, that you are looking only at PCB, but there may be many other contaminants in the sediment, like pesticides and other organic molecules.
Sure.
So,
of course, there are many contaminants, but PCB is the most toxic one. The real coming issue comes. It is because of the fishing industry. That's the problem. As you know, in the fish tissue, they are very fatty. As most of the fat, and actually supposed to be healthy for you. The fish, eating fish and fatty fish, it's healthy. Salmon, for example. But the problem came, especially in the salmon now. They found a lot of PCB in the tissue of the salmon. See, that's really coming issue, because PCB is different. Yes, there are many toxic materials there, but PCB is actually because the hydrophobicity of it. That's really the problem. So as I said, even the polar bear. I mean, can you believe this? Polar bear in the Alaska and the far away, still the PCB transform from here to because it has a very high capability of it transforming. Now, actually, the Canadian government has a small, big lab in not small actually, big lab in Halifax. I probably know Halifax. It's far away. In Canada, in the north, and that lab is just to concentrate on looking at the PCB. Yeah, okay. It's really issues. But again, as I said, PCB goes to the fish a lot, and that's why in the Hudson River you are not allowed now to do fishing that much. Actually, unless you have to go to the north of it, because of the PCB. That's why the concentration was on the PCB.
Okay, thank you. And how realistic it is to treat such a large quantity of sediments from Hudson?
That's a great question. And again, because of the electron accelerators. With the 80 kilowatt machine, with the 80 kilowatt machine electron accelerator, even if the energy is low, like 3 or 4 MeV, it's fine. Okay, but with the machine, you could, as I said, the late Marshall Cleland, I mean, we put a proposal to the state of New York to put the electron beam accelerator on a barger, okay, and pump sediment from this side over the other side, but through electron to irradiate. And as I shown you that the reaction rate constant is extremely fast, and so you could do dechlorination extremely fast with a very short time. Let's talk about microsecond. Okay, and then of course, so the residency of the slurries of the sediment in front of the beam is going to be very short. In that case, it means that you could really literally pump millions and millions of liters of sediments from this side to other side in the front of the electrons.
Okay. Thank you so much.
Yeah, you're welcome.
All the best. Yeah.
Çevrimiçi katılımcılardan İbrahim Tokul'un bir sorusu var ama İbrahim Bey duyuyor musunuz beni? Zaman kısıtı olduğu için soruları yazabilirsiniz. Sonrasında tekrar sorulara dönüş yapılacaktır. Thank you, Professor, for your presentation and collaboration.
You're welcome. Thank you so much. Greeting from here, from United States, to all of you.
Saat farkından dolayı son sunumumuz Profesör Doktor Pilari'nin sunumu yarın yapılacak. Yarın 9.15'te burada olabilirsek 9.20'de sunum başlayacak. O yüzden ona dikkat edersek seviniriz. Tomorrow the presentation will begin 9:20. Teşekkürler, iyi akşamlar.
Alacağım.